All right, everybody, welcome. Today's speaker is Dr. Edward C. Norton, the United Healthcare Professor of Healthcare Management at the University of Michigan. And his talk today will help us, one, to understand why one should almost never report odds ratios, and two, his talk will help us to understand the one case where reporting odds ratios makes sense, and three, his talk will help us to understand alternative ways to present results from logistic regression. My name is Jeffrey Hotch. I am the Associate Director for the Center for Healthcare Policy and Research. It's my job to welcome you to today's seminar series. This is the CHPR seminar series. For some of you, for others, it is EPI 291, and for others, it is an opportunity to get continuing medical education. Welcome, all of you. We're so glad you're here. There may be some technical details in today's talk, but the main points are incredibly important. So just focus on those. They are, one, we cannot compare odds ratios. And the other main point you might want to take home is our analysis result when we do, let's say, logistic regression, when we're looking at logit estimates, our main result is a ratio, not the item of interest itself, but a ratio. And this means that odds ratios apply to that data set and that model specification only, but no other. Yikes. So we are so excited to hear from our speaker today, Dr. Norton. He is a real nonlinear thinker with findings that have clear and direct implications. Dr. Norton, take it away.
Thank you very much. Really appreciate that introduction. And let me see if I can get my slides up. All right, can you see the cover slide? Great.
Yeah.
So I had very much been looking forward to giving this talk a few months ago, and then I had a personal health crisis. That means I got COVID, and so was not able to do this, but we were able to reschedule for today. So very excited to be with you virtually, and hope this is a clear talk that gives you some new ideas on how to interpret results from logistic regression and give you some new ideas. So yeah, first what I want to do is just start talking about when you have a binary outcome and you want to understand or express the strength of association between some right-hand side variables and the outcome, there's several ways to do it. We can talk about probabilities, we can talk about odds or odds ratios, which I'll do a lot today. There's also risk and risk ratio, risk difference, marginal effects. And my goal today is to try and provide some insight into the really deep interpretation of odds ratios, as well as their limitations, and provide some alternatives to odds ratios. So first, some background to make sure we're all on the same page. The odds are the ratio of the probability that the outcome does occur to the probability that it does not occur. So you could think of this as P divided by 1 minus P. Those are odds. So for example, if the probability of going to a hospital in a year is 20% or 0.2, then the odds of going to the hospital are 0.2 divided by 0.8 or a quarter. We could also express it the other way around, that if the probability of not going to the hospital is 80%, then the odds of not going to the hospital are 0.8 divided by 0.2 or 4. Okay, a few more things about odds. If P is really small, then the odds are about equal to P because the denominator is very close to 1. But as P gets larger, then odds and probabilities diverge. Probabilities, of course, are bounded between 0 and 1, whereas there is no upper limit on odds. They can be extremely high if the probability is extremely high. And one thing to keep in mind is the wonderfully oxymoronic phrase, even odds. And that's the odds are 1 when the probability is a half. And of course, odds can never be negative. That's a little bit of background. If you're a gambler, you would be very familiar with odds. So for example, if I had a fair deck of cards, I shuffled them up and we gambled on the probability that a randomly selected card is a spade as opposed to any of the other suits, well, the probability of that is 25%, 13 divided by 52, and therefore the odds of selecting a spade are 13 divided by 39, the 39 non-spade cards, so 1 to 3. And one way to think about this then is if I bet $1 on the outcome of this, I would need a payoff of $3 for the basically 3 chances of not getting a spade to every 1 chance of getting a spade. That would be a break-even bet. Okay, but we're not going to talk about gambling today. We're going to talk about logistic regression. So I need to convert everything into logistic regression. Hopefully this will be familiar to most of you. The outcome we want to think of as being either 0 or 1, some sort of binary outcome. It could be pass or fail, live or die, readmitted to the hospital in 30 days, not readmitted to the hospital in 30 days, any sort of binary outcome. And we'll typically want to model that probability not just as a single parameter p, but as a function of a whole bunch of interesting covariates, maybe policy variables, maybe personal characteristics, maybe hospital characteristics or school characteristics. And so here I'll use the shorthand x prime beta to just represent a whole linear index of a bunch of right-hand side variables and their associated parameters. So we have a constant term beta naught and beta 1 times x1, beta 2 times x2, and so forth. And the function 1 over 1 plus e to the minus x beta is a wonderful mathematical function that is bounded between 0 and 1. It can never go negative, and it can never be greater than 1. And this is the logistic function. And so we can model the probability as a function of these x characteristics, and we'll always get a nice probability bounded by 0 and 1. Okay, if we do that, and we say we run a logistic model in Stata or some other software, it will give out estimated values of all of the betas. How do we interpret those betas? All right, so a couple ways to do this. The beta by itself is a little challenging because it's not a probability on its own, nor is it an odds ratio on its own. It's something called a log odds, which is really weird. So let's think about this. If x is a binary variable, say a 0, 1 variable, as well as y, then the odds ratio you can think of as exponentiating its coefficient beta. So for example, if beta is 0.4, e raised to the 0.4 is about 1.5. So its odds ratio would be 1.5. If beta is about 0, this is the even odds situation, then the odds ratio is 1. And if beta is negative 0.2, then the odds ratio will be less than 1 at 0.82. Anytime beta is really small, then the odds ratio is about 1 plus beta, which is a convenient thing to remember. Okay, so that's how we can convert betas into odds ratios by exponentiating them. So a little more about odds ratio. It gets the name because it can be a useful concept when comparing two groups represented by a right-hand side variable. So very often treatment versus control. You might have smoker compared to non-smoker or diabetic compared to non-diabetic. And so we could have an outcome like probability of mortality, and we want to compare smokers and non-smokers. So we get a probability for the smokers, we get a probability for the non-smokers. And then the odds ratio is a ratio of two odds. First, the odds for the smokers, say in the numerator. So you have a probability for smokers divided by 1 minus the probability for the smokers. And the denominator is same, but for the non-smokers. And that, as it turns out, is exactly equal to e raised to the beta for smoking in a logistic regression. So that one coefficient is actually numerically equal to this ratio of four values, two different kinds of probabilities. And it gives some indication um, of the risk, whether the risk is more or less likely for one group and another. So if you have, say, an odds ratio of mortality for smokers compared to non-smokers, and let's say that that odds ratio is bigger than 1, then that would tell you that the risk of dying is higher for smokers than for non-smokers. Okay, we can be a little more precise, but one is very much the relevant thing for, is it more or less likely for the one group compared to the other. Let's go through a specific example. This is based on a paper published in JAMA about 8 years ago by Tringale and co-authors. They studied industry payments to physicians. And so just taking their numbers, just over half of the male physicians received an industry payment, whereas only 42.6% of the women physicians received an industry payment. So given those numbers, we can calculate the odds for men, which is just over 1, and the odds for women is about 0.74. And then we can take the ratio of those two odds to get an odds ratio for men compared to women is about 1.39. Okay, that's not adjusting for anything, that's just using the numbers there. And so we can say that the odds that men receive industry payment is about 40% higher for men than for women. Now, men and women don't go into medical specialties at the same rate, and not all specialties have the same probability of having industry payment. So it's quite possible that industry payments could be influenced by things like which specialty you go in, and perhaps other factors. So they controlled for a whole slew of other factors. And after they did that, they got an odds ratio of a little bit different. It was 1.28, but still much higher for men than for women. Okay, so that's one example from the literature. And we saw that in this case, adding more covariates reduced the odds ratio from about 1.4 to about just under 1.3. We'll see that that doesn't always happen. Okay, so hopefully that was review for most of you. And now I want to talk about two problems with odds ratio. The first one is just a matter of interpretation and sometimes confusion between odds or odds ratios and probabilities. They're not the same thing. When the probabilities are really small, they're very close. When the probabilities are not small, then they're not close at all. Some people find this confusing. If you're really familiar, though, with logistic regression and odds ratios, you've probably gotten quite used to them. But for non-scientists, for people who don't have an epi background or not used to this, it's just very confusing to read, say, a newspaper article and keep track of whether something is an odds ratio, a probability, a risk. That those terms are a little hard for a lot of people to understand. Now, this is a well-known problem in the literature. One of the things that would be a mistake in the Tringale et al. Paper would be to say men are 40% more likely to get industry payments. That's not true. The odds are 40% larger for men than for women, which is a different statement than men are 40% more likely. Just the difference between odds and probabilities. Another thing about odds ratios are it's extremely helpful whenever talking about odds to also give the underlying probability. For example, if I just tell you that the odds ratio for treatment compared to control is 2, that is true both for very small probability cases, like when the underlying probability is 1% for treatment and only 0.5% for control, But it's also true for 50% for treatment, 33% for control, or 80% for treatment and 67% for control. Those sets of probabilities, if you do the calculation, all have the same odds ratio of 2. So when reporting results, it's always helpful to say, well, I have an odds ratio of 2 and the underlying probability is either really small or medium or high, whatever the number is. That also goes for things like marginal effects or risk ratios. Okay, but most of my talk is going to be about this second problem with odds ratios, which is less well known. And that is that the odds ratios are scaled by a seemingly arbitrary factor, which is the square root of the variance of the unexplained part of the binary outcome. So that's a big expression, and I'm going to walk through this. I'm going to try and give a couple of ways of thinking about this. Again, depending on your background, I'll show this mathematically. I'll try and provide some intuition. I'll go through some examples. So hopefully, no matter what your background, you'll see several different ways to think about it. And hopefully some of what I say will click and make sense. So my simple monetary metaphor here is, suppose that someone listed prices, let's say Amazon listed prices on its website for goods that you wanted to buy, but it didn't list the currency. It didn't say whether it was dollars or pounds or euros or yuan or any other currency. It just said, you know, the price is 42 or the price is 87, but you didn't know what the actual currency was. In a way, that's the metaphor you want to think of with odds and odds ratios, because part of what's being reported, you don't know what it is. And this arbitrary scaling matters. And it matters, the way that's easiest to understand is when you add or subtract variables from the right-hand side model specification in a logistic regression. When you add additional variables, those variables presumably help explain some of the underlying variation in the dependent variable, and therefore less of it is unexplained. And when you therefore add more variables, that will actually end up increasing the odds ratio, even if those extra variables are completely independent of the other variables. And again, I will go through some examples here. So if that didn't quite make sense, hang on. So there's some important consequences of this. I'm foreshadowing some other slides later in the talk. There's no such thing as like a unique odds ratio, like the odds ratio for any particular study. The odds ratio is conditional on not only that sample from a data set, but also that model specification. And therefore, it cannot be compared to an odds ratio either from the same study using a different model specification or from one study to another. You just cannot compare odds ratios. They have different scaling factors. They cannot be compared in terms of magnitude. So let's go to ordinary least squares regression to get some intuition for what I'm talking about here. So let's imagine that we have now not a binary dependent variable, but a continuous dependent variable. We'll call it y star. And let's say that we have 3 explanatory variables, very creatively named x1, x2, and x3. And there's, of course, an error term, and the variance of that error term is sigma squared. So sigma squared represents the amount of variation in the original dependent variable that is not explained by the x's. And so we know that if we add additional variables that are independent of the other x's, sigma squared will go down and the r squared will go up. Okay. The key thing here is that these all need to be independent of the other x's. So the betas from the original smaller specification stay the same. We add additional variables. the R squared goes up, sigma squared goes down. You can think about running 4 separate regressions, first on just a constant term, then on just x1, then add in x2, then add in x3. And as we do this, the R squared will go up, sigma squared will go down. And if x1, 2, and 3 are unrelated to each other, then all of the estimates for beta 1 will be the same. The estimates for beta 2 will be the same. Adding additional variables won't change those estimates. Let me show you one example based on real simulated data. This is from our health services research paper if you want to look it up later. Each column here represents a separate regression. The left column is the simpler regression. There's a constant term and 3 covariates with coefficients about equal to 0.05, 0.1, and 0.2. And then the second regression adds 2 more variables with coefficients about equal to 0.1 and 0.3. When we add those variables, we see that the R squared goes up a lot from about 0.2 to 0.6, and the root mean squared error, or the square root of the variance, we'll call it sigma, that goes down from 0.45 down to 0.32. But if you look across the pairs of coefficients that are circled in light blue, those coefficients stay about the same. They're about 0.05, 0.1, 0.2. There's really no change when we add those variables. Keep that in mind. This is foreshadowing for later. Because now we want to think about, well, what happens when we switch from ordinary least squares regression and now go to logit? Does the same thing apply? Do we have the same outcome where the betas stay about the same when we add additional variables, or does something else happen? And so to do this, we're going to have what's called a latent variable framework, and we're going to show one way to derive logistic regression out of a least squares regression with a continuous variable where we have a threshold. So we start again with our continuous variable y star. You could run a nice least squares regression with that. But let's say we cared about whether the dependent variable was above or below a threshold. So for medical terms, you could think of whether or not someone has high blood pressure or not. That depends on their actual blood pressure, which is a very continuous variable. But if it's above or below a certain threshold, like 180, then we may declare someone as having either high blood pressure or not. We could do this with BMI. We could do this with AIDS. We could do this with all sorts of measures based on a continuous underlying biological phenomenon. Birth weight for babies. Some babies, if they're below 1,500 grams, are declared to be very low birth weight, or below 2,500 grams are declared to be low birth weight. But there's a continuous variable underneath that. So if y is above or below t, some threshold, we may instead want to have this binary outcome, low birth weight or not. So we can rewrite the least squares regression in the following way. Instead of y star equals x beta, we can write it as, what's the probability that y star is, say, above a threshold, that birth weight is above 2,500 grams? Well, that's the same as the probability that x beta plus epsilon is bigger than t, or that, rearranging terms, epsilon is bigger than t minus x beta, or again, rewriting, if we assume that the error term has a symmetric distribution, then we can go from the second line to the third line and just flip signs around. That probability that epsilon is less than the opposite value by symmetry. And then we're going to do the following. We're going to standardize the error by dividing the standard, by dividing that expression by the standard deviation, which we'll call sigma, because statisticians can make really precise statements about standardized distributions. Think of the standard normal distribution, where 2.5% of the probability is either above 1.96 or below minus 1.96. Statements like that. So we're going to take that expression, the probability that y star is above a threshold is the probability that its error term is below this other expression as a function of the x's. We're going to divide by sigma, and then we can make statements about precise probabilities using logistic formula, or if you want to go probe it and normal distribution, we can do that. Okay, this sounds innocuous, and in most textbooks, right after saying, well, we're going to standardize this and divide by sigma, it's, well, let's just assume sigma is equal to 1 and we'll carry on and basically forget about it. It sounds innocuous. What could possibly go wrong? My kids have learned when I tell stories, or when my kids were young and I would tell stories, they knew that when I said, what could possibly go wrong, that was the time to really pay attention. Their eyes would get big and they'd lean forward and they get all excited because they knew something was about to go spectacularly wrong. Okay, so what's going to go wrong here is that what we're going to do is we're going to leave sigma in all of the expressions from now on. All the expressions that, if you're familiar with logistic regression, will look familiar, except now I'm going to keep sigma in there. Okay, so one way to express the probability that the continuous variable is above a threshold is something like 1 over 1 plus e to the minus x beta over sigma. We're going to leave sigma in there, even though we can't really observe it. And this also means that if we go back to odds, remember odds, p over 1 minus p, we're now going to rewrite that in terms of beta and in terms of sigma. And what you'll see is that sigma no longer disappears. So the odds you can write as p over 1 minus p. If you put in a bunch of math, the logistic function is wonderful because things cancel out very nicely. And if you look at this formula long enough, you'll realize that it simplifies down to e to the x beta over sigma. Or we can write this specifically in terms of odds for a smoker compared to odds for a non-smoker. And again, if you go through all the math, we'll see that the log odds are equal to the coefficient beta for smoking over sigma. So what's different now than a few slides ago is, instead of saying beta is the log odds, I'm saying that beta over sigma is the log odds. And this is really going to matter because we don't know what sigma is. Okay, logistic regression estimates beta over sigma, but we don't know what sigma is. And that's going to cause some interesting things. Okay, so how does this matter then? Okay, sigma is a measure of the unexplained variation. If we add variables to the model, we've seen in least squares regression that sigma goes down. Well, if sigma shrinks, then beta over sigma should get bigger. And so there's several implications that are important of the fact that logistic regression estimates beta over sigma, not beta. As I said before, there's no single odds ratio. The odds ratio is conditional on your data set and the sample from that data set, and it's conditional on the model specification. And so it doesn't make sense to say I estimated the odds ratio, because it's totally conditional on the sample and the model. The odds ratio shows the sign and some sort of magnitude, but it's much harder to interpret. So in addition, if you cannot compare odds ratios off across different model specifications or across different data sets. They're just, it's like comparing temperature in Fahrenheit with temperature in centigrade or temperature in some other system that you don't know how to calibrate. It's just that they're different scales, but you don't know what the scales are. It is fairly common in applied work to show several different models using the same data set with related model specification where you add in additional variables. Now, we saw this with the Tringale article. And the idea is to add more variables, see if the results are robust, or perhaps by putting in more variables, some of them are confounders, they're correlated, say, with treatment, and then you want to control for more things. But in logistic regression, you really can't compare the odds ratio from those models directly because you expect that beta over sigma to be different, even when you add variables that are independent of the treatment. Okay, so these points are unfortunately not really widely appreciated, although there's gradually becoming a better understanding of this. Papers still frequently report odds ratios as if they were an absolute number without explaining that they're conditioning on the model and the model specification. And now, before you walk out of here and say, oh, he said that odds ratios have no meaning. No, that's not right at all. They have an extremely precise meaning. It's an odds ratio that applies to that data set and that model specification only, but no other. Okay? It's a very precise meaning. It has a lot of meaning, but it just doesn't generalize, unfortunately. I'm going to try telling you a little sort of story to try and give you some more intuition about how to think about what I just said. Sometimes this intuition works, sometimes it doesn't, but let me try and do it. And then I'll go on and show you a numerical example. Suppose that you were trying, that you had data on lots of people and you wanted to test whether someone tested positive for COVID or not. So it's a binary outcome. You either test positive for COVID or not. And you're primarily interested in whether someone is vaccinated or not. But of course, there are lots of other reasons why someone might test positive or not for COVID. If someone lives completely alone, they're a hermit on a deserted island, they're not going to get COVID no matter what because they have no contact with other people, right? So it doesn't matter whether they're vaccinated. There are others that may have had COVID recently and so are basically immune and will not test positive for COVID because they had it a few months ago. There are other people who may have gotten vaccinated in the past, but the vaccination wears off. Everybody has their own story for whether they test positive for COVID or not. There are lots of different reasons, who you come in contact with, the prevalence of COVID, the time of year, there's seasonality, lots of different things going on. We have one very simple variable we're trying to use to explain whether or not someone gets COVID. Suppose you start with the population of the entire world. You get 8 billion people in your regression. There's lots of stuff going on. That one variable, are you vaccinated, is going to explain a little bit, but it doesn't explain a lot. What if we start adding controls? Adding controls that really explain whether or not this person, that person actually tests positive for COVID. We put in covariates for, are you a hermit? Do you live alone? Are you isolated? We put in other controls for whether you've had COVID recently, for whether you interact with lots of other people, lots of other explanations. As you put in really good covariates that explain what's going on for individuals, In logistic regression, you can add in variables in such a way that they become perfect predictors. You basically remove those observations out of the model. As you remove observations out of the model, what you have remaining in your model um, is a more and more homogeneous population for whom all the other explanations don't matter, and for whom the only remaining possibility for whether or not you have COVID is, are you vaccinated or not? But you've removed lots of the population of the world. You have a much smaller, much more homogeneous population. And initially, the variable, are you vaccinated or not, may explain a little bit. As you remove observations from your data set because you can explain them with other factors very well, the vaccination or not becomes a really strong predictor of that much smaller, more homogeneous population. And so the idea there is that as you add more variables to explain, you're explaining more and more of the variation in the dependent variable, and what's left for that one remaining variable being vaccinated is beta over a smaller and smaller sigma. That variable will get much bigger and bigger and bigger as you are explaining the remaining variation for a smaller population. Hopefully that helps at least some people. Before I show you an example, I will tell you that there are cases where odds ratios very much are appropriate, and that is for case control studies. Epidemiology has a rich history of doing case control studies where you have matched populations that are either identical or very similar on X covariates, and people are matched up. Here's this 32-year-old male smoker and a 32-year-old male non-smoker that are the same on sort of everything we can measure. When you have case-controlled studies, you no longer have a population that's entirely representative. You have this odd yet wonderful paired up data set. And basically, then the only thing that's different between one half of the data and the other is whether or not they're a smoker. And in those cases, case-controlled studies, you really can't, at least not very easily, calculate marginal effects or other things. Odds ratios are the appropriate interpretation. For the economists in the crowd, this is known as the Chamberlain conditional logit model with fixed effects. So just do keep that in mind. Odds ratios sometimes are appropriate. I think that's why they have remained so popular in epidemiology. There are cases, but then they get applied to other situations which are not case controlled. All right, so having said that, there are other ways of expressing the strength of the association, including marginal effects. And one of the wonderful things about marginal effects is that they are not sensitive to changes in sigma. So if you calculate marginal effects and calculate odds ratios as you add more variables in a logistic regression, marginal effects stay constant and odds ratios will blow up. And so this is a reason, I think, to prefer marginal effects, which are going to be just about constant when you add additional non-confounders compared to odds ratios. So a marginal effect has the interpretation of a percentage point change. So, for example, smokers compared to non-smokers have a, let's say, 10 percentage point increase in mortality by age 50 or something like that. Okay, so now I'm going to show you an example where of what happens to both the odds ratios and the marginal effects when we add more independent variables. And we'll see in this example that the odds ratios increase, marginal effects stay the same. It's building off of the previous table I told you about. So the left side of this slide you've already seen before. That the first two columns are for a linear regression or linear probability model. The right side is taking the same data and estimating two logistic regressions. And if you compare what's going on, in the blue, we have the either IE, the incremental effect for dummy variable, or the ME, the marginal effect for continuous variable. And you see in the third and fourth columns that those are just about the same, going from about 0.05 to 0.05, 0.1 to 0.1, from 0.2 to 0.2. So the marginal effects are the same, whereas when we add in X3 and X4, the odds ratios blow up from about 1.3 to 2.3, from 1.7 to 6.3, and from 2.7 all the way up to almost 39. So these are pretty strong examples. They don't always change this dramatically. This was to prove a point, but this does show a case where if you add in additional variables that are uncorrelated with the variables that are already in the model, in OLS you get no change in the betas. In logistic, you get a change in beta over sigma, but not in the underlying marginal effects. Finally, if you've heard of entropy balance, this is a wonderful way of reweighting the data. Typically, reweight the control sample such that the X variables for the control match the X variables for the treated group in things like mean and variance. Entropy balance can be used with a logistic regression. That's absolutely fine. But if you do that, then again, you have the same kind of situation. Whereas, let me put it this way. If you do entropy balance and run ordinary least squares, then say on treatment, so you have outcome on treatment, it doesn't matter if you add in the additional covariates when they're entropy balanced, because they are effective. All the covariates are effectively orthogonal to treatment. It's like reproducing the perfect randomized control trial. So in OLS, the betas stay the same. If you entropy balance in logistic regression, it does matter whether or not you include those extra covariates. The marginal effect, again, will stay about the same, but the estimated odds ratio will increase when you add in the extra covariates. All right, so in conclusion, odds ratios are often reported without the proper discussion of how they are conditioned on that data set and that model specification. And you cannot compare odds ratios across models, across samples. They have different scaling factors. Again, it's like comparing the temperature from different temperature scales where you don't know actually what the scale is. Logistic regression estimates beta over sigma, not just beta. And instead, I would recommend that you estimate marginal effects, which are not sensitive to changes in sigma. So, and here I have references. If you want copies of the slides, you can send email to Jeffrey Hotch. He has a copy of these. And I'm happy to open this up to questions. You've all been very patient and very quiet.
Thank you, Dr. Norton. We really appreciate you communicating this. We have some biostatistician people who I am sure may have a thing or two to say. There are also perhaps some more practical applied researcher people who may have some questions as well. Everyone should feel free and comfortable to ask a question. And you can put it in the chat. You can do the actual raising the hand by turning on your camera like Dan has, or you could do the virtual raise your hand if you'd like. And I'm seeing cameras going on, which I might interpret. Oh, and I see a hand going up. Dr. Kravitz, would you like to ask a question to Professor Norton?
I would, yeah. First, great set of papers and really clear statistical talk, which unfortunately is a rarer thing than one might like. But you know, someone who's been in the health services research field for 30 plus years, why are we only hearing about this now?
I don't know. And I do also want to say that I and my co-authors are not the only ones who've ever tried to point this out. There are a number of other papers. We try and cite them in our papers. I've one of the other authors, I think it was Allison, I remember reading on their website saying they had tried to publish this in a sociology journal and just kept getting turned down, sort of desk rejected because their interpretation was nobody wanted to hear this. So I think well, I'm not exactly sure why, because I think there are fairly straightforward alternatives. My guess is that the way this has been, odds ratios have been taught, logistic regression has been taught, people feel comfortable with it. They know it, they've seen it, they read about it. And again, in some cases, again, coming out of a very rich tradition in epidemiology, there are cases where it is absolutely the right thing to do. And my guess is that over time, people went from correctly applying this case-controlled studies to, well, I'm familiar with this, I'll apply it to other situations. That is my guess, although I don't know, I'm not an epidemiologist.
Super. Dan, I see you looking ready to ask a question.
Well,
Be nice.
that was a terrific presentation, Professor Norton.
Thank you.
There was a famous epidemiologist who complained how when Daniel McFadden and James Heckman got the Nobel Prize, that the technology for the choice-based, sample-dependent corrections is exactly the same as used for case control studies. And why don't they give us statisticians these Nobel Prizes? So I just start off with that observation. The specific case control study you talked about is actually what we would in epidemiology call a match case control study.
Yes, that's
And
correct.
A useful way to think about what the proper effect size estimate or what the proper model would be is what is the true estimate of interest? If there truly is a single odds ratio that describes for two people that are otherwise similar what the change in odds would be, and that would apply across a very heterogeneous population, then the best way to estimate that is, the control in a highly stratified manner for all of those characteristics. The marginal effect would also be different in that situation. So the marginal effect, the way you described it as impervious to that, you said it was not affected by the other covariates, but your papers actually correctly say it's not as affected. We can construct pathological examples where the marginal effect would be very affected depending on what subsets of a very heterogeneous population were included, where a fixed odds ratio would apply, and therefore the marginal effects would very much differ across the different subpopulations.
So two things. The papers are careful to say are close to or nearly the same because of these are non-linear approximations basically, right. and you're never going to get it sort of numerically the same due to the non-linearities. The other thing I'd love to know more about what you're talking about. I'm wondering is if what you're saying that if there are heterogeneous marginal effects, then trying to estimate a single marginal effect when there are actually multiple marginal effects for different subpopulations, then yes, that would be a problem.
Right,
I
but
okay.
it's inherent in the model specification. Like if we say that an odds ratio is 2, and that applied to a very broad spectrum, a pair of patients where the controls rate is 1%, the patient with the risk factor would have the odds ratio of 2 would basically translate to a 2 percentage point incident. Whereas it would be 2 over 90, 2 over 101.
It's basically 2 to 1.
Whereas if another patient was in a different substratum of the population and their baseline risk was 50%, an odds ratio of 2 for that person would correspond to a probability of 2 over 3, which would be 66% for the exposed person. So that difference in the risk probability would now be 16 percentage points, not 1 percentage point.
Correct, but that would be a different subpopulation. So I think that is assuming that is a case where the marginal effects are heterogeneous across subpopulations.
Right, but in that case, in that example, the odds ratio is still the same. And so it's really a question of what model is the correct model. Is it a model where there's an odds ratio that applies across a broad swath, or is it a model where the percentage point difference is applicable across that population?
I'm not sure what it means to have the odds ratio be the same. I'm not sure how you construct that if you have additional covariates that you can add that are actually predictive of anything. I think you would end up with different odds ratios in that case.
Well, I mean, you can set up a hypothetical example where you posit that this is the odds ratio with all of the variables that are applicable. This turns out to be a fixed odds ratio.
Yes,
and then
you can do
instead of
that.
adding covariates, what statisticians would want to do is subtract out covariates and see what happens when you have omitted variable bias.
And then the odds ratios will change.
Exactly.
Yes.
And that would be that's the problem. The problem is you're
Yeah.
misestimating the model.
Yes, that's
and-
okay. That's a different problem
Yeah.
when you see, and we tried to be very careful about only talking about variables that were not confounders.
Right.
Okay, because if you have variables that are confounded, it's a completely different set of problems.
Right, exactly.
Yeah.
There's a couple of other things that I just want to quickly say that
Good.
are part of what's so super valuable about your study. Your presentation. One, I would caution against you saying that it's specific to the sample. It's really specific to the population. There is a such thing as a sampling distribution for a logistic regression or an odds ratio estimation. You may personally think that, no, it's tied to the sample because of that fact that there's a fixed variance estimate for the probit or for the logit, but that little sample variation not exactly hitting what that true known variation is, which is pi square over 3 for a logit and 1 for a probit, doesn't necessarily affect the odds ratio estimate. So it's really, you're right that the odds ratio is very much conditional on what's in the model, and that is very much emphasized in our epidemiological text. And it's also specific to the population, not to the sample per se, but to the population.
Okay. I see the point you're making. Yeah. That makes sense. Yeah.
And then the two other just real quick things. The reason why the odds ratio has become so popular is something you'd appreciate as an economist. It was shown that when you do a prospective study, and this is part of the complaint with the epidemiologist and why did the economists get the Nobel Prizes? The only thing that's wrong with doing a prospective logistic regression calculation on case control data is your intercept term is off, but the odds ratios themselves are magically corrected for those problems. So odds ratios become very popular in epidemiology because they work with both prospective and retrospective data. That's one thing. And then another use case that is really important about the very important example you're pointing out is that when you in social sciences do mediation analyses, you'll just adjust for the mediator and see how the coefficients for the variable of interest changes. You can't do that with a binary outcome, and it's specifically because of the important problem that you described here.
Yeah.
The fact that when you include covariates, whether those covariates are or are not associated with another independent variable of interest, it's naturally going to change the coefficients because there's that fixed variance term. So that's just something to add as an additional consideration as why what you're talking about is such an important thing for people to know when they're doing analysis.
Good. Thank you for your comments. I think there are other people.
Yes, thank you. Sorry about that. We've got just 1 minute left. I wanted to make sure I could get Dr. Morrison to briefly share his chat and then get your final thoughts, Dr. Norton.
Yeah, this is probably just a notation question. So I've heard what I think is the same thing described as omitted covariate bias, and I think Dan said that word too. Is this the same thing or is it a different thing?
We focus on adding and subtracting covariates that are unrelated, they're independent of the other variables in the model. If they are correlated and are therefore confounders is another word, or endogenous, that raises additional problems.
Yeah, that the confounding makes sense, but
Yes.
at least what I've seen, omitted covariate bias, it is for uncorrelated predictors.
Yeah, it is omitted variable bias. Professor Norton, the difference between a GEE model where you have a marginal interpretation versus a random effects model for a logistic regression, there's attenuation in the odds ratio. And the assumption, of course, is that the random effects are totally independent of the predictors. That, of course, is never true in real life, but that's the assumption.
Yep.
So the reason why you have that attenuation is because of what we call in epidemiology omitted variable bias. I know in economics you guys also have that term, but we don't require that there be correlation.
Super. Dr. Norton, in 10 seconds or less, can you give us final thoughts for today? What we should leave if, say, Greek is not our first language, what we should leave today with having appreciated your talk and maybe wanting to have a bottom line. What are the final thoughts for today?
Be very careful about interpreting results from logistic regression.
Yeah.
And I hear you saying that's true, not only if I'm comparing one study to another study, but you're telling me be careful even if I make two different models, like a simple model and a fancy model with the same data.
Right.
Is that right?
Yes.
Yikes. Thank you so much for coming today, having a robust discussion and a fascinating talk, helping us appreciate this. We've got the papers that we can check. Are you okay if we follow up if we have questions?
Absolutely.
Super.
Absolutely.
Thank you so much for sharing your research with us today, Professor Norton. We really appreciate it.
Thank you very much.
Bye for now. Thank you,
Bye.
everyone, for attending.